Project 3.3.1 Chump Code Clock and Counter.
This is my circuit for the clock. So basically, the A-stable 555 right here oscillates the LED, and the frequency is determined by the potentiometer. Here is the monostable 555 where if I press a button, as long as I hold the button, the LED will be on, and the button is debounced using the 555. And here's the bistable 555, where if the switch is high, the LED will be high, and if the switch is low, the LED will be low. And this is also debounced using the 555. And this is the final output LED connected to all the other outputs of the LEDs using the inverter and or OR gates. It performs a task where if this switch is low, the bistable LED 555 is low, this LED will mimic whatever this LED does. And if it is high, it will mimic whatever the A-stable LED does.
This is my circuit diagram for the A-stable 555. The three 5K resistors in series inside the 555 causes the voltage to be split into 3 equal parts, which causes the external capacitor right here to fill up to 2/3 the way full, which pulls the latch low, and then it will start draining until it is only 1/3 the way full, and then that pulls the latch high. This creates an oscillating output right here for the external LED connected to it. This is my circuit diagram for the monostable 555. So basically I have this button right here, and when I press it, this capacitor will fill up, and then it will not reset the switch until this capacitor is completely filled. So whenever I press a button, there will be only one signal sending to the LED, which debounces it. And the time that it takes for the capacitor to charge can be determined using the resistor and the capacitor using this formula right here, where T is in seconds, R is the resistance in ohms, and C is the capacitance in farads. This is my circuit diagram for the bistable 555. So we have the switch right here, which controls this LED, and that will bounce a little bit when it is actual wiring using hardware. So by utilizing this SR latch inside the 555, no matter how many times it bounces, since it is a latch, it will still only produce one signal. And all of these debouncing for the switch and the button is basically to minimize the amount of errors that the clock pulse will have. This is my circuit diagram with all of the 555 circuits along with the final logic gates added to get in final LED output. So since the bistable is high, it will end with the A-stable with the OR gate, and it will go to the AND gate right here to the end, so the LED will mimic what the A-stable does. When I flick the switch, the bistable will be low, which turns using this inverter will turn this end high, so whenever I press the button, the LED will turn high at the final LED. And this is the halt button, where if I make it high, it will no longer do anything, no matter what the other ones are.
This is a circuit for the program counter. So basically the clock pulse created from the previous circuit goes into the clock pin of the program counter, and that counts these 4 LEDs in binary. And you can use the A-stable 555 pulse from here, or when you switch your switch, you can just manually step it up. And this button is to clear the counting, and this switch is to halt the entire LED. So as you can see, the A-stable is pulsing, but the final 4 LEDs right here are not counting at all. When I flick it back, it goes back to normal. And these 2 buttons use an AND gate and an inverter to simulate a NAND gate. And so basically these 2 go into the load pin of the PC. And when both of them are pressed, it will make these 4 LEDs match whatever is on the switch. So when I press these 4, it will match this. And if I change the switch a little bit, say something like this, it will also match the switch. This basically sets a specific step for the program to whatever the switch is.